It begins with a question that has followed humanity like a quiet shadow. Why does the universe so often present us with mysteries that contradict our intuition? This question sits at the heart of nearly every scientific paradox, offering not just puzzles to be solved, but windows into the limits of our understanding. Before the first equation is written or the first theory is named, there is that simple, unsettling moment when the world refuses to behave the way we expect. And in that refusal, something profound is revealed about us, our assumptions, our hopes, and our desire to anchor ourselves in a cosmos that rarely grants certainty. Imagine a dimly lit study late at night. Books lie open in uneven stacks. Notes are scattered in half-legible scrawls. A scientist sits alone, staring at a page that should make logical sense, but doesn't. Outside, the world continues its quiet rhythm. Traffic hums, trees rustle in the wind, distant voices fade into the night. But inside that room, a storm of contradictions begins to form. A cat that can be both alive and dead. A traveler who rewrites his own existence. A sky that should shine with endless light, but instead offers darkness. These paradoxes aren't just intellectual curiosities. They shake the foundations of how we think reality is supposed to work. Every era has faced its own version of this tension. For the ancient Greeks, motion itself seemed impossible once scrutinized closely enough. For early cosmologists, the night sky posed a contradiction that pointed toward an expanding universe long before anyone could measure it. For modern physicists, the fabric of space and time strains under conflicting theories that both claim to describe the truth. And for philosophers and technologists, the very nature of consciousness and reality raises unsettling possibilities about where and what we truly are. The paradoxes that surround us do more than challenge scientific models. They compel us to confront our assumptions about cause and effect, about beginnings and endings, about free will and inevitability. They remind us that the universe is not obligated to align with human intuition. And yet, in the dance between contradiction and explanation, something uniquely human emerges, the desire to make meaning out of confusion. This is the story of that desire, a journey through 14 chapters, each centered on a paradox that has shaped our understanding of reality. Not simply a technical explanation, though the science will be there. Not simply a historical retelling, though the discoveries and the thinkers behind them will appear. But a deeper exploration of what it feels like to exist in a world where certainty is rare and mystery is abundant. Think of this as a documentary told through scenes of human curiosity. A researcher standing before a chalkboard filled with impossible equations. A thinker staring out at the stars in quiet frustration. An astronaut imagining the strange elasticity of time. A philosopher holding a mirror to our assumptions about existence. These images will guide us as we explore puzzles that have resisted simple answers for centuries. In the end, each paradox reveals something not just about the universe, but about us. Our hunger for clarity, our discomfort with uncertainty, our resilience in the face of the unknown. And the paradox at the heart of inquiry itself, the more we learn, the more we discover how much we have yet to understand. So we begin with a question, a simple one, an ancient one, a deeply human one. What happens when the universe refuses to obey the rules we think it should? The pursuit of that question is our prologue, and the journey ahead invites us to wander into the places where logic fractures, certainty dissolves, and understanding becomes something earned rather than assumed. What if you could build a machine that let you slip through time like flipping pages in a book? What if you could go back, not just to witness, but to intervene? That's the premise that launches one of the most haunting questions in all of physics, the grandfather paradox. Picture this: a brilliant inventor, driven by wonder or grief or a stubborn need to fix the past, constructs a time machine. Not a glowing fantasy device, but something tangible, humming with strange energy. They step inside and vanish into the past, hoping to change something small or perhaps something monumental. And there, in that forgotten decade, they encounter a young man who will one day be their grandfather. A mistake is made, an accident or a choice. And the young man dies before ever having children. Here's where the loop begins to tighten. If the grandfather dies, the inventor is never born. But if the inventor is never born, they never travel back in time, which means the grandfather survives, which means the inventor is born. Which means the paradox is not just a story device, it is a mathematical knot, a contradiction that breaks causality, the fundamental rule that says every effect must have a cause. This kind of recursive logic spirals endlessly, a Mobius strip of impossibility that has confounded thinkers for decades. Is time travel into the past truly impossible? Or is our understanding of cause and effect too rigid for the reality we live in? There are escape hatches, theoretical doors left ajar by physics. One of them is the Novikov self-consistency principle. It suggests that the universe is stubbornly self-preserving. You can travel to the past, yes, but you cannot change it in any way that creates a paradox. If you try to harm your grandfather, the gun will jam. You'll trip. You'll change your mind. The universe conspires in absurd and poetic ways to protect the integrity of the timeline. In this model, the past is not a blank slate but a locked archive. You're not a god. You're a tourist. Then there's a wilder alternative, the many worlds interpretation. In this view, every quantum event splits reality into parallel timelines. When you kill your grandfather, you don't undo your own birth. You create a new branch of reality where you were never born, while your original timeline continues untouched. You're now marooned in a universe that has no memory of you, no place for you to return. You exist, but not where you began. These theories don't just stretch our understanding of physics. They force us to confront something more personal, the fragility of memory, the irreversibility of time, the longing to rewrite the past. The grandfather paradox is a mirror that shows us the cost of tampering with history, not just in logic, but in identity. If changing the past means erasing yourself, what is the value of intervention? And perhaps that's the deeper truth behind the paradox. Not that time travel is forbidden, but that consequence is inescapable. Every action, every intention echoes forward and backward in ways we cannot fully predict. So the next time you find yourself thinking about the one moment you would change, ask instead, what would it change in you? Because maybe the real paradox is not in time, but in the human heart's relentless yearning to undo what has already been lived. It started with a lunch conversation in 1950. A group of physicists sat in the Los Alamos cafeteria, their trays barely touched, as the topic drifted from nuclear weapons to the cosmos. Then suddenly, a voice cut through the chatter, sharp, bewildered, almost impatient. "Where is everybody?" The man was Enrico Fermi, and his question, simple yet devastating, became the seed of what we now call the Fermi paradox. In a universe that has existed for nearly 14 billion years, with hundreds of billions of galaxies each containing billions of stars and likely trillions of planets, why haven't we found any sign of intelligent life? We have the tools. Radio telescopes scan the skies, space probes venture outward, and yet the silence is absolute. Not a whisper, not a flicker. No messages, no monuments, no ruins, just an endless void. This absence is not merely disappointing, it's statistically shocking. Given the vastness of time and space, even the most conservative estimates suggest we should have detected something. A signal, a probe, a cosmic signature. The void isn't empty, it's screaming with possibility. And yet it gives us nothing in return. One explanation is almost comforting. We are first. The spark of life, the leap to consciousness, the mastery of technology, perhaps these are so staggeringly rare that Earth is the only place they've happened. If that's true, we are the universe's first awakening. The lonely pioneers of awareness, charting a galaxy that has never known thought before us. But another possibility is darker. What if civilizations are common, but none survive long enough to reach us? This is the idea of the Great Filter, a barrier that most intelligent species fail to cross. Maybe they destroy themselves with war or technology. Maybe they collapse under the weight of their own complexity. Maybe intelligence itself is a self-terminating trait. If the Great Filter is behind us, we are lucky beyond belief. But if it lies ahead, then every advance we celebrate may bring us closer to the same fate as those who came before. The silence becomes not a mystery, but a warning. Other theories attempt to sidestep the grim logic. The zoo hypothesis suggests that we are being watched but not contacted, like animals in a preserve. Perhaps advanced civilizations see us as too primitive or too dangerous to engage. There is also the dark forest theory. In a universe teeming with life, the only safe strategy is silence. Shout into the void, and you may draw the attention of something that sees you as a threat. These ideas are unsettling not because they are strange, but because they feel plausible. They echo the same instincts we've honed on Earth: caution, concealment, survival. Perhaps the galaxy is full of watchers, not speakers, predators, not neighbors, and yet here we are, sending signals, building telescopes, searching for an echo in the darkness. The Fermi paradox forces us to question not only the cosmos, but our place in it. Are we special? Are we doomed? Are we just early? Or are we already too late? In the quiet hum of radio waves, in the blinking lights of distant observatories, we continue to ask, not because we expect an answer, but because asking reminds us that we are still here, still listening, still hoping. Why is the night sky dark? It seems like a child's question, innocent and obvious. But for centuries, this simple inquiry defied explanation. If the universe is infinite, filled with stars, and has existed forever, then every direction we look should eventually land on a star. The sky, logically, should blaze with light. Night should be as bright as day. This is Olbers' paradox, named after the German astronomer Heinrich Olbers, though the puzzle haunted thinkers long before him. It's a contradiction that strikes at the very structure of the cosmos. If space is infinite and eternal, then why isn't the night sky a sea of fire? Imagine standing in a forest so vast that no matter where you turn, your sight ends on a tree trunk. Now imagine replacing those trees with stars. Every line of sight should end in light. The darkness we see should not exist, but it does, profoundly, beautifully. And that darkness tells us something essential about the universe. The first clue lies in time. The universe, we now know, is not eternal. It has a birthday, roughly 13.8 billion years ago. That means light from anything farther than 13.8 billion light-years simply hasn't had time to reach us. There are stars and galaxies out there, but their light is still en route, sailing through the void unseen. The second clue is motion. The universe isn't static, it's expanding, and that expansion stretches space itself. As it stretches, it pulls the light traveling through it into longer, redder wavelengths. The most distant galaxies are receding from us so rapidly that their light is stretched beyond the visible spectrum, into infrared and microwaves, where our eyes can't see it. This red shift robs distant starlight of its brilliance. Some of it is still there, yes, but ghost-like, faint, haunting. What remains visible is filtered through the lens of time and cosmic motion. The result? Darkness. So the blackness of the night sky isn't empty. It's pregnant with history. It holds the memory of light that hasn't arrived, and light that has been stretched thin across billions of years. In fact, the faint afterglow of the Big Bang itself, the cosmic microwave background, is still detectable today with sensitive instruments. The darkness isn't silent, it's whispering. Olber's paradox, then, isn't a flaw in our logic. It's a revelation. It tells us that the universe had a beginning, that it evolves, that what we see is limited not by our imagination, but by the speed of light and the shape of time. Every starless patch of night is a map of the unknown, a reminder that our view of the cosmos is finite, a slice of a much larger whole. So the next time you stand beneath a dark sky, don't see emptiness. See distance. See youth. See the frontier of the visible. And let the darkness be not absence, but invitation. There's a cat, there's a box, and there's a paradox that has haunted science for nearly a century. Schrödinger's cat is more than a thought experiment. It's a philosophical grenade lobbed into the foundations of quantum mechanics. At its heart lies a simple, terrifying idea that until something is observed, it may exist in multiple states at once. Not one or the other, but both. Picture this scene. A sealed box. Inside, a cat, unaware of its place in history. Alongside it, a radioactive atom with a 50-50 chance of decaying in the next hour. If it decays, a mechanism triggers a vial of poison to shatter. If it doesn't, the cat lives. Outside the box, you wait. The hour passes. The box remains closed. In the world of classical logic, the cat is either alive or dead. You just don't know which. But in the quantum world, something far stranger is proposed. Until the box is opened and the state is measured, the cat is simultaneously alive and dead, both outcomes held in a fragile, ghostly balance called superposition. This idea wasn't meant to comfort. Erwin Schrödinger proposed it to highlight the absurdity of applying quantum theory, which works exquisitely for particles, to everyday objects. He was troubled by the implication that reality doesn't settle into a definite state until it is observed. And yet, experiment after experiment supports this very idea. According to the Copenhagen interpretation, it is the act of observation that collapses the wave of probabilities into one outcome. Until then, the system remains unresolved, a paradox not just of logic, but of being. But what is an observation? Does it require a human mind, a camera, a passing particle? This is the measurement problem, and it remains one of the deepest mysteries in science. Some escape the paradox through the many worlds interpretation. In this model, opening the box doesn't collapse reality. It splits it. In one universe, the cat lives. In another, it dies. Both outcomes are real, each inhabiting its own branch of an endlessly dividing multiverse. The cat was never both dead and alive. It simply followed two divergent fates. This solves the paradox, but at a cost. It replaces mystery with multiplication, suggesting that every quantum event spawns entire new universes. A staggering price for logical consistency. Yet the heart of Schrödinger's cat isn't about physics alone. It's about our discomfort with uncertainty, our need to define the world in absolutes. It challenges our sense of control, of observation as understanding. It asks, can you live with ambiguity? Can you accept that reality, at its deepest level, is a matter of possibility? The cat in the box is more than a metaphor. It's a mirror. It reflects our struggle to reconcile what we see with what is. It shows us that knowledge is not always illumination. Sometimes it is the very act of opening the box and choosing to look that creates the truth we find inside. A rocket waits on the launch pad, sleek and silver against the twilight. Inside, one of two twins sits ready for departure. Let's call him Bob. The other, Alice, stands below, waving. Same DNA, same birthday, but their paths are about to diverge in a way that defies our common sense. This is the twin paradox, one of the most famous consequences of Einstein's theory of special relativity. It's not a hypothetical, it's not science fiction, it's physics. Verified, tested, and as counterintuitive as anything in the cosmos. Bob's journey begins with fire. The engines roar. He accelerates to near the speed of light, hurtling through space toward a distant star. For him, time feels normal. Seconds tick by steadily. But back on Earth, something strange is happening. To Alice, and to every clock on the planet, Bob's time is running slower, much slower. After a few years of travel, Bob turns around and returns, again at nearly light speed. When he lands and steps out of his ship, he expects to see Alice just a little older. But she's not. She's aged decades. He's aged only a few years. Time, it turns out, is not absolute. It bends, stretches, and compresses depending on your speed. The faster you move, the slower time passes for you relative to others. This isn't theory. It's been confirmed by flying atomic clocks on jets, by GPS satellites, by experiments with particles. It's real, and it's deeply unsettling. The paradox arises when you ask, from Bob's point of view, wasn't he stationary in his ship while the Earth sped away and came back? Shouldn't Alice have aged less from his perspective? Isn't motion relative? Yes and no. Here's the key: acceleration. Bob changes frames when he turns around. He feels force. He experiences a break in uniform motion. Alice, by contrast, stays in a single inertial frame the whole time. This asymmetry resolves the paradox. It's not just speed that matters, but changes in motion. The one who accelerates, the traveler, ages less. And that's what makes it a paradox worth reflecting on. Not because it breaks the rules, but because it obeys them in a way that breaks our expectations. It reveals a universe where time is not a shared river flowing uniformly for all, but a winding stream that can fork, slow, or rush ahead, depending on the path you take. Einstein once said that the distinction between past, present, and future is a stubbornly persistent illusion. The twin paradox shows us just how fragile that illusion is. It invites us to reconsider what it means to age, to wait, to return. If time is elastic, then so is memory, connection, even love. What happens to a relationship when one person lives through decades and the other through only moments? And if we could outrun time, what would we choose to leave behind? In the still silence between Earth and stars, the question lingers. Is time our anchor or our illusion? Try to walk across a room. Now imagine this. Before you can reach the other side, you must first reach the halfway point. Then you must reach halfway of what remains, and again and again. Each step halved, each distance shrinking but never quite disappearing. By this logic, motion itself should be impossible. You can never reach your destination, because there's always another fraction to cross. This is Zeno's paradox. It doesn't just question motion, it weaponizes infinity. In the 5th century BCE, the Greek philosopher Zeno of Elea proposed a series of puzzles that challenged the very foundation of how we perceive space and time. In another version, Achilles races a tortoise. The swift warrior gives the slow creature a head start. But as Achilles runs to where the tortoise began, the tortoise has moved a bit farther. When Achilles reaches that new point, the tortoise has inched forward again. The gap shrinks, but never disappears. Achilles, it seems, can never win. For over 2 millennia, these paradoxes baffled mathematicians and philosophers. They hinted at something deeply unsettling. That infinity, once invited into logic, could unravel reality. The answer would not come until the birth of calculus in the 17th century. Newton and Leibniz introduced a powerful new way to think about change, not as an infinite process, but as a sum of infinitesimally small parts. In this view, an infinite number of steps can still add up to a finite distance. The paradox is resolved not by denying motion, but by understanding how infinity can converge. Take the series 1/2 plus 1/4 plus 1, 8 plus 1, 16. It continues forever, but its sum is exactly 1. This is the key. The infinite is not always endless. It can be bounded, manageable, real. Zeno's challenge wasn't mathematical in nature. It was philosophical. He dared us to think deeply about what it means to move, to measure, to progress. He showed that even our most basic intuitions can be illusions, crumbling under the weight of precision. And isn't that still true today? Our digital world thrives on the calculus Zeno never knew. Every animation, every simulation, every algorithm slicing time into frames, space into pixels, built on the logic of the infinite made finite. But Zeno's ghost lingers. It reminds us that the world we see is not the world as it is. That between any 2 points lies an unseeable infinity. That our movement through life, toward goals, through moments, across years, is both continuous and composed of countless steps, each as real as the whole. Perhaps in the end, Zeno didn't want to stop us from walking. He wanted us to feel what it means to take a single step and understand the infinite miracle hidden within it. There's a melody in the air, faint, familiar, a symphony from the past. But where did it come from? Who wrote it? This is the riddle at the heart of the bootstrap paradox, a thought experiment that breaks the idea of origin. In this paradox, an object, a piece of information, or even a person exists without ever having been created. It exists in a loop, passed through time, without beginning or end. Imagine a time traveler obsessed with Beethoven. He journeys to the past, sheet music in hand, desperate to meet the composer. But when he arrives, he discovers the unimaginable. Beethoven never existed. There is no music, no notes, no name. So the traveler publishes the music himself. He becomes Beethoven. Centuries later, inspired by that music, another version of himself travels back in time to do the same. So who composed the symphonies? No one. Or everyone. The music exists. It has always existed, but it has no origin, no first composer. It simply loops. This is the bootstrap paradox, named after the idea of pulling oneself up by their own bootstraps, doing the impossible. It violates everything we believe about causality. We expect every effect to have a cause, every creation to have a creator. But here, the loop closes with no entry point. Take it further. Imagine a pocket watch passed from an older man to his younger self via time travel. The younger man keeps it for life, then gives it back to his younger self again. The watch never wears down. It is pristine, eternal. But when was it built? Where did it come from? Now the laws of physics start to scream. The second law of thermodynamics says that disorder, or entropy, must increase. A watch passed through an infinite loop should degrade. It should scratch, rust, decay, but in the paradox it doesn't. It remains untouched by time, even as it loops through it. This forces a deeper question. Is such a loop possible, or is it a violation of physical law? Is the universe built to prevent such orphaned causality? Or is there something we still don't understand about time and information? Some physicists believe these loops are forbidden. Others suggest they might be allowed under certain exotic conditions, like traversable wormholes or closed time-like curves, but all agree. If they're real, they challenge the very fabric of logic. And beyond the science lies something more poetic, the question of authorship. In a loop without origin, who owns an idea? Who deserves credit? If creation is just repetition across time, then where does inspiration truly live? The bootstrap paradox leaves us not just confused, but humbled. It whispers of stories and songs and souls that might exist without beginning. That maybe, just maybe, some truths don't come from anywhere. They just are. And perhaps the greatest mystery is not where they began, but why we feel such a need to ask. There is a place in the universe where light goes in but never comes out, a region so dense, so extreme, that even the laws of physics begin to unravel. This is the black hole, a marvel of gravity and mystery. And within it lies a paradox that has shaken the foundations of science, the black hole information paradox. Start with a simple truth from quantum mechanics. Information cannot be destroyed. Burn a book and its contents dissolve into smoke, ash, and heat. But the arrangement of atoms, the information, is still there, scrambled but recoverable in theory. Now toss that book into a black hole. Cross the event horizon, the point of no return. According to Einstein's general relativity, the book, and every atom in it, is gone forever, sucked into the singularity, its information sealed off from the universe. But here comes the twist. In the 1970s, Stephen Hawking discovered that black holes are not truly black. Thanks to quantum effects at the event horizon, they slowly emit radiation, now called Hawking radiation, and over unfathomable spans of time they evaporate, disappear, leaving nothing behind. So what happened to the information? If it's lost, quantum theory, one of the most successful frameworks in science, breaks. But if it escapes, then Einstein's black hole, a cosmic prison, was never truly secure. This is the paradox, two titans of physics, two truths that cannot coexist. Over decades, physicists have proposed daring solutions. Some suggest that information is somehow encoded in the Hawking radiation itself, a vast, complex pattern hidden in what once seemed like pure noise. Others believe in the holographic principle, that all the information falling into a black hole is stored, not lost, on the two-dimensional surface of the event horizon, like a cosmic hard drive. If true, this principle could apply not just to black holes, but to the entire universe. Our three-dimensional world might be a projection from a distant surface, a hologram, a metaphor made literal. Still others propose more radical ideas, firewalls of energy at the edge of black holes, or quantum entanglement bridges between the inside and outside, what some call ER-EPR. The stakes are not small. The resolution to this paradox could unlock the holy grail of modern physics, a unified theory that merges general relativity with quantum mechanics, a theory of everything. And yet, for all the equations and theories, the heart of the paradox is deeply human. It asks, can knowledge truly vanish? Is anything ever forgotten by the universe? Or is there a memory woven into the cosmos itself, a ledger that records every thought, every act, every particle's path? To look into a black hole is to look into the edge of understanding, a place where light, time, and certainty dissolve. And perhaps in that dissolution we begin to glimpse not just the limits of physics, but the limits of what it means to know. Picture a scientist in a sterile white room watching a subject through a pane of glass. Every gesture, every blink, carefully noted. But something feels off. The subject shifts, fidgets, glances back at the glass. The act of being observed is changing the behavior being studied. This is the observer's paradox. In social science, it's a familiar challenge. Observation alters reality. The moment we study something, we influence it. But in quantum physics, this idea is not just a methodological quirk, it's a fundamental truth. At the subatomic level, particles don't behave like tiny marbles. They exist as wave functions, clouds of probability representing all the possible states they could occupy. An electron isn't here or there. It's potentially everywhere until it's measured. The moment we observe it, the wave function collapses. The particle snaps into a single position or momentum. The act of measurement creates the outcome. This isn't a flaw in our tools. It's not about clumsy equipment. It's a feature of the universe. Reality, at its core, is participatory. The Heisenberg uncertainty principle makes this even clearer. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It's not just hard to know both, it's impossible. Nature itself has encoded uncertainty into its fabric. This leads to a haunting question. What does it mean to observe? Is a conscious human mind required? Could a camera collapse the wave function? A passing photon? A blade of grass? The answer is still debated, but the implication is clear. The universe is not a passive backdrop waiting to be revealed. It responds to attention. It becomes definite only when engaged. In one interpretation, this gives rise to a kind of quantum solipsism. Until you look, the moon might not be there. Until you measure, the particle might not exist in any particular place. It's not that the universe is unreal, but that it is unfinished until noticed. Some have taken this idea to spiritual extremes, suggesting that consciousness itself is the foundation of reality. Others urge caution. Quantum mechanics may be strange, but it does not grant us magical powers. And yet, the paradox remains deeply human. We seek to understand the world, but in doing so, we change it. We chase objective truth, knowing that our presence colors the outcome. We long to observe purely, but we cannot separate the seer from the seen. Perhaps that's the hidden insight of the observer's paradox. That knowledge is not detached, but entangled. That understanding something means becoming part of its story. And in a world where even atoms respond to our questions, perhaps the deepest truth is this. Reality is not just something we find, it's something we help shape. There's a question that sounds absurd, even childish, but its implications reach into the very heart of existence. What if everything we know is a simulation? This is not science fiction. It's the simulation argument, a philosophical paradox sharpened into a razor by Oxford philosopher Nick Bostrom. He proposed a trilemma, a set of three possibilities. One of them, he said, must be true. First, advanced civilizations like ours almost never survive. Something stops them: war, climate, artificial intelligence, apathy. They vanish before gaining the power to simulate conscious beings. Second, such civilizations do survive, but they choose not to simulate us. Perhaps they find it unethical, or boring, or irrelevant. They look back at their primitive past, our present, and decide it's not worth recreating. Third, we are almost certainly living in a simulation, a constructed reality so complete, so immersive that we can't distinguish it from the real. This third option is the most unsettling. If even one advanced civilization runs ancestor simulations, digital recreations of their past, then they could run thousands, millions, even trillions of them. Each simulation could contain billions of conscious entities like us. Statistically, the number of simulated minds would vastly outnumber the original biological ones. So the logic goes, it's overwhelmingly likely that we are one of the simulated. The paradox here isn't just technical, it's existential. If our universe is a simulation, what does that say about our lives? Our choices? Our pain? If every star is code, every memory an algorithm, are we still real? Some suggest yes. Because real or simulated, our experiences feel genuine. Love still moves us. Loss still scars. Joy still erupts without warning. If the simulation is perfect, then from our perspective, it makes no difference. But the thought lingers. Could there be glitches in the code? Unexplainable events? Coincidences too sharp to be chance? Or is the simulation so flawless that it erases all evidence of itself? The simulation hypothesis also brushes against theology. If someone built this universe, who are they? Programmers? Gods? Curious post-humans studying their digital ancestors. Skeptics point out that we have no proof, only speculation. But the power of the paradox lies not in evidence, but in probability. It forces us to confront the possibility that everything we take for granted could be fabricated. Still, even in that dizzying possibility, a strange comfort emerges. Whether we are real or rendered, the human experience remains profound. The sun still warms our skin. Music still stirs emotion. The night sky still invites wonder. So maybe the simulation argument isn't a crisis, but a mirror. It reflects our need to question, to understand, to seek meaning. And perhaps the real paradox isn't whether we are simulated, but that we care so deeply about the answer. In a quiet corner of the universe, everything seems still. But beneath that stillness lies the strangest truth. We may not be seeing all that is there. We may be missing not just objects, but entire layers of existence. Welcome to the paradox of hidden dimensions. Modern physics, particularly string theory, suggests that the universe may have more dimensions than we experience. Not just the familiar 3 of space and 1 of time, but 10 or 11 in total, perhaps more. Most of these are curled up, compactified, folded into invisibility. Like the width of a sheet of paper viewed edge-on, they evade our senses. Why believe in dimensions we cannot see? Because some of our most powerful equations, those that aim to unify gravity with quantum mechanics, require them. Without these extra dimensions, the math doesn't work. With them, it begins to sing. In these hidden dimensions, gravity may leak. Forces may unify. Particles may vibrate differently. Like strings in a grand, unseen symphony. The universe becomes not a flat, silent canvas, but a multidimensional orchestra. The paradox is this: we might live in a reality far richer than what we can observe. We move through 4 dimensions like fish in water, unaware of the vast sky above. We think we see the whole, but we may only grasp a slice. And yet these invisible dimensions are not fantasy. They have fingerprints, the behavior of particles at the smallest scales, the nature of dark matter, the subtle warping of space-time. Physicists build machines like the Large Hadron Collider, not just to smash atoms, but to glimpse beyond the veil. Still, skepticism remains. Some argue that dimensions we cannot detect may not be real. Others press on, seeking indirect signs, shadows of a deeper structure, hints that space itself may be woven from something finer than we imagined. This isn't the first time science has expanded our vision. There was a time when the Earth seemed flat, when the stars seemed fixed, when only what could be touched or seen was thought to be real. But history reminds us, reality often hides in plain sight, waiting for new eyes. So we listen, we measure, we dream. Because if these hidden dimensions are real, they may hold the answers to the deepest questions. Why does gravity behave so differently from the other forces? What is the true shape of the universe? Why is there something rather than nothing? And perhaps most hauntingly, what else is out there, just beyond the limits of perception, waiting to be known? The stars above twinkle with ancient light, and deep below that sky, the human mind turns over one last riddle. One that threads through every paradox we've explored. What does it mean to know? Knowledge feels absolute, a fixed point. But again and again, the universe has shown us that knowledge is not only incomplete, it's often shaped by the very act of asking. Our tools, our observations, even our existence alter the answers. This brings us to a final puzzle, not from physics or philosophy alone, but from the very nature of inquiry, the paradox of self-reference. Imagine a book that says on its cover, "Everything in this book is false." If that statement is true, then the book is false, which makes the statement false, which makes it true, and so on. a loop with no resolution. The paradox lies not in the content, but in the structure of the statement itself. In science, self-reference appears in systems that try to describe themselves. In logic, Gödel's incompleteness theorems show that any system complex enough to contain arithmetic will have truths it cannot prove using its own rules. There will always be questions that lie just beyond the reach of formal logic. In computation, Alan Turing proved that some problems cannot be solved by any algorithm. There will always be programs that can't be predicted without running them. Reality, in this light, becomes something we can never fully simulate, never fully contain. And in consciousness, the ultimate self-referential system, the paradox becomes deeply personal. We are minds trying to understand minds, beings trying to define being. The observer observing the act of observation. This is not failure, it's revelation. The paradoxes we've explored, from cats and clocks to black holes and simulations, are not roadblocks. They are signposts. Each one says, the universe is more than what you see. Reality is not a closed book, but a living question. And so, we end not with a solution, but with a shift in perspective. Perhaps the goal is not to solve every paradox, but to let them shape the way we ask. To remain curious, to stay open, to wonder, even when answers remain just out of reach. Because in the quiet between contradictions, something extraordinary happens. We grow. The stars are still above us. The questions are still unanswered. And yet, something is different. We've journeyed through the paradoxes that define the edges of what we know, from the loops of time and the silence of space, to the strange rules of atoms and the haunting possibility that nothing is as it seems. We've asked if reality is fixed or participatory, if time can be bent, if existence might be coded. And in each case, the universe answered not with certainty, but with a riddle. So what now? We step back and see the larger pattern. Each paradox, each contradiction is not a dead end. It is an invitation, a mirror that reflects both the strangeness of the cosmos and the depths of human inquiry. Because what makes these paradoxes so enduring isn't just their scientific implications. It's how they resonate with something older, more intimate, our need to understand ourselves. We want the past to be changeable because we carry regret. We want to find others in the universe because we fear being alone. We imagine infinite timelines and simulated worlds because we ache for purpose in a seemingly indifferent cosmos. Science, at its best, doesn't just give us tools or technologies. It gives us language for our longings. It lets us frame the unframeable, touch the untouchable, think the unthinkable. And yes, sometimes it leaves us with paradoxes, those strange, unsolvable knots that remind us of our limits, but also our reach, because paradoxes are where certainty ends and imagination begins. They are the threshold between what we can explain and what we can only wonder at. They remind us that knowledge is not a destination but a journey, one defined not by answers but by the courage to keep asking. So we return to the night sky, not to solve it, but to stand beneath it in awe. And we ask one final time, what if the universe is not a puzzle to be solved, but a story to be lived, one paradox at a time,